Chances are, if you were ever in grade school, you've probably seen something like this. It's not new, but we can do this. Just to add this 3 plus 8, 1, carry the 1, and then you add those. Math. Addition. But sometimes these addition problems can be bigger, or sometimes not even addition. Sometimes they're multiplication. So what we've done as a society is we've made these things, and these do all the hard work for us if you want to be lazy, and we are lazy. So we made these, but how do these take in a number like 7 plus 8, and then how does it do that? How does it output that number with just electricity? Well, that's what we're going to be talking about today. So in order to understand how computers add numbers, we're going to need to understand two concepts: number bases and logic gates. Number bases are essentially what we count with. So we typically count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have base 10 because we have 10 values to choose from. But computers can't tell electricity 9 and expect it to do something. So typically we use what's called binary, or zeros and 1s. So base 2. Now you're probably thinking, well, how do you count with zeros and 1s? Doesn't make sense. And let's think about how we count with 0 through 9. So first we go 0. We go 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, since we can't go above 9, we add a 1 to over here, and then we make this part a 0, and we repeat through it again. So how we count with zeros and 1s is we do this. We go 0, 1, but we can't go above 1, so we go 1, 0. Then we go 1, 1, but we can't go above 1 here, so we carry the 1 over, make it a 0, and keep going. So 1, 0, 1, 1, 1, 0, 1, 1, 1, and down like this. Now, before we continue to more things about binary, let's talk about number places. So, if you have a decimal number, over here you have your 1s, you go up and it's times 10. So now you have your 10s, times 10 again. You have your hundreds, then times 10 again, you have your thousands. So each time you go up over here, right, it's times 10 every time you move to the left. So, that's, you'll see why that's important later. So, and if you notice, this is also the same number as the base. So this is base 10, you times 10 every time you move to a new place. Now, you can also rewrite this number out like this. You can write it as 2 times 1,000. Sorry, well, I can write math. 2 times 1,000 plus 3 times 100 plus 7 times 10 plus 6 times 1. And, that's a way you can expand it out into its places. Your 1s, your 10s, your 100s, your 1000s. All right. Now that we have an understanding of how that works, I hope I explained that well, we can also apply the same thing for binary. So let's say we have the number 1001. Now, this is going to be our ones place, just like a decimal. So ones. But if you remember when we were counting, when we go 1 and then 1, 0, if this is 1, this means that this right here is 2. So 1, 0 is 2. So if we count through binary, that means that this place over here is going to be our 2s. So, times 2 each time we go up. So that means that this area is our 4s. Over here is going to be our 8s. So that's pretty neat. If, you know, we can now use that for doing the same thing up here. So if we were to do the same thing up here, we take our base, so 8, times whatever's there, so 1, plus 0 times whatever place it's in, so that's in our 4s. 4s, so 4 times 0, 2 times 0, plus 1 times 1. Simplifying this, we get 8 plus 1, or 9. So that means that this binary number is equal to 9. Okay, so now let's talk about logic gates. So logic gates take one or more bits as inputs and spit out one bit as an output. So there are 4 simple logic gates. There is the NOT gate, the OR gate, the AND gate, and the XOR gate. The NOT gate essentially inverts whatever the input is. So if the input is going to be a 0, the output's going to be a 1. But if the input's a 1, the output's going to be a 0. OR gates are on if either of the inputs are on. If input A or input B are on, the output is also going to be on. AND gates are on only if both inputs are on. So if A and B are on, then there will be an output. XOR gates are a little bit funky, in that they're on if either input are on, but if both inputs are on, the output is off. These are going to come in handy if we're going to design a calculator. Alrighty, now that we have a decent idea of how logic gates work and you know what they do, they take a few bits as inputs and then they output a bit as an output. Now we're going to apply we're going to see how these connect to binary and how we add binary numbers. So I'm going to do a magic trick. I'm going to change the page. Magic. So let's take a look at this sum chart. So this is the 2 bits being added, A and B, and we're going to have 2 outputs to these 2 numbers. We're going to have the sum, which is what they add to, and then we're going to have the carryout. So remember, if we have a 1 plus 1, 2 bits, that's going to be 1, 0, but we have to carry the 1. So we're going to have 2 outputs. We're going to have the sum and the carryout. So let's take a look at the addition of A and B. So let's look at the sum. So if we add 0 plus 0, if A and B are both 0, the output is 0. 0 and 1, the output is 1. 1 and 0, the output is also 1. 1 and 1, the output is 0. If this should be ringing a few bells, because this is an XOR gate. So this right here is an XOR gate if A and B are the inputs to the XOR. Then if we look at the carryout, it's off the entire time unless both inputs are on. So this is an AND gate. So now we can actually build a logic circuit, and this is what it looks like. So we have our XOR gate, which is our sum if from our input A and B, and then we also have our carryout, which is going to be the AND gate. Now this is really good if we want to add 2 bits, but we don't want to just add 2 bits, because 2 bits is just upwards to, we can only add up to the number 2. And a calculator that can only go up to 2 isn't going to be very useful. So we need to figure out how to get more bits into this. Now the first thing we can think about is, if we're going to go over to the next, the next space in our addition question here, is we're going to need to add the corresponding bits to those, but we're also going to need to add in the carryout from the previous value. So we're actually going to need 2 adders. So we're going to need 2 of these. So I'll show you what that looks like in just a second. Alright, so this is an adder including carry in and everything. So this is what we call a full adder. And I know what you're thinking, that's a little bit scary, right? But if you break it down into little parts, it makes a lot more sense. So we have our half adder up here just for reference. So right here is our half adder. If you draw a little line, over here is our half adder. Now, this half adder goes into another half adder where we add the sum of a and b plus the carry in. So the total sum that we get from this is a plus b plus the value that we carry in from the last adder. And the reason that these are so good is you can actually, if you were to bring this carry out and bring it into another adder, you'd be able to basically go down a wall of adders, and you'd basically be able to add any binary number as big or as small as you want with ease because they're so modular. So the carry out can go into the carry in of the next one, and then so on and so forth. Now, I really wanted to demonstrate this, and I do own electronics, so I could go put something like that up downstairs and show a circuit of it, but that doesn't give an intuitive understanding. So instead, I came up with a better solution. So for the 5 of you who don't know what Minecraft is a game where you can either survive, build things, or watch the world burn. But I'm not going to get into any of those elements. Minecraft has something called redstone, and redstone is essentially electricity that can allow you to turn lights on, push objects, or other things. But it can also be used to create the logic gates that we've been talking about this entire time, such as the NOT gate, the OR gate, the AND gate, and the XOR gate. Alright, so this is our calculator. So this can add up a 2-bit binary number, and we can actually see some parallels here. So the red ones are XOR gates, the blue ones are AND gates, and the green one is an OR gate. So up here we have our half adder. Then down here we have 2 half adders, and this half adder is being put into this half adder, which goes into the OR gate, and this is our carryout. So let's do an experiment, shall we? So let's try 0, 1, or 1 plus 0, 1, 1 plus 1. As we see, 1 plus 1 is equal to 1, 0, or 2. Let's do 1 plus 3, which will be 1, 0, 0 for 4. So 1 plus 3, 1, 0, 0. Also, so that's how computers add numbers. I hope you enjoyed. Also, just as a footnote, anybody who's interested in computer science and who owns this game, I'd highly recommend doing this. It's honestly really good. It's a really good way to learn it, and it's also a really fun way to learn it too. So, anyways, that'll be it. Pretty gnarly, eh?